Hello everyone. Before starting this session, let me revise a few concepts in real analysis that you have already learned. The concept of limit suprimum and limit infimum. In this session, let me revise the concepts. For any sequence En, suppose if I have a sequence En in a set of real numbers R, we can define a limit suprimum and limit infimum. And it is given by, let me define limit suprimum as limit n tending to infinity, suprimum of a sequence En as intersection of union. That is, an intersection of union of all the sequence is none other than a suprimum of that particular sequence. Similarly, limit infimum is defined as limit n tending to infinity, infimum of En is equal to union of intersection. It is just the reverse of a suprimum. Fine. Remember, these are all key points that you should know in order to continue the next theorem. So in order to do the next theorem, all these basic concepts should be in your mind. So first one is that when I said limit suprimum, it is intersection of union. Similarly, when I said limit infimum, it is union of intersection. And next, whenever you're going to prove the theorems in measure and integration, I'll tell you the key point just for your reference in order to remember. Suppose if you're having a theorem related to infimum, fine. In such case, you have to take intersection of open sets. It is just a key point. You have to take intersection of whatever the sets given in a particular theorem. And if you're dealing with a theorem related to infimum, fine. If you're dealing with the theorem directly related to measurable sets on infimum, I'm repeating once again, measurable sets on infimum, then you're going to consider just for an infimum increasingly sequence condition. In the previous session I have told you, you have to consider a sequence is monotonically increasing. For infimum case, you have to consider this sequence condition, that is infinitely increasing sequence condition. And the next thing is that suppose if in a theorem you're going to take, for this reference only, infimum reference, if you're going to take a set F as intersection of all EI's, then you can rewrite this condition as Fn is subset of En plus k. As F is equal to EI, there will be one En in this collection such that F is contained. In the sense, F will be there in one of the set, at least in this collection. So from these two I can write that En will be subset of En plus k. Remember, I am talking about infimum. You have to remember all this condition in the proof. Fine. Again, further if you are going to take measure for the above condition, you are going to write measure restricted measure Fn will be less than or equal to, I can directly take infimum for this. Infimum of some particular k into measure of En plus k. Clear? So En plus k, I can directly take E infimum and measure with that. Fine. Moreover, further if you are going to simplify this, in the sense, in any of the simplification, if you are going to get a term like this, and when you're going to apply limit for this particular term, like limit n tending to infinity, I can rewrite this as infimum of k values. For all k values greater than infinity, I can rewrite En plus k as En. I'm repeating once again. Suppose if you're going to simplify any step like this, I'm applying limit n tending to infinity for this particular step. So if you're doing that, for all values of k greater than infinity, I can rewrite En plus k as En. This is first key point. Similarly, suppose when you're dealing with suprimum case, I'll tell you the same in case of suprimum. Fine. When you're dealing with the theorems which contains suprimum, in such case you have to take union. I'll tell you just for comparison. In such case, I have to take union. And further, you are going to consider monotonically decreasing sequence condition. That is, Fn is reversing. That is, if I can rewrite this as Fn plus 1 will be contained in Fn. Fine. Further, if you are going to assume this condition, that is, if you are going to take F as intersection of all the sets, then as per this condition, I can write all Fn's will be contained in En plus k. Just the reverse of this. Clear? Further, I can rewrite this statement as En plus k will be contained in Fn. Fine. Again, when you are going to apply measure, for this term you are going to apply measure directly. Whereas for this term, since you are dealing with suprimum, you have to take suprimum over k into measure of En plus k. Clear? Further, if you are finding limit with this, in the sense if you are going to apply limit this with this, I have already told you, I can write this as limit n tending to infinity, suprimum of, for all k values greater than infinity, this En plus k will become En. These are all properties you have already learnt in real analysis, just a recapitulation of that. Fine. You have to remember these key points. Now, by using these key points, let me prove one theorem. Here I have a theorem statement. Fine. Anyhow, I will send you the definition of limit infimum and limit suprimum. Don't worry about that. But all the key points I cannot send you. I cannot make a note of that. That is all basics which you are already learnt in a real analysis. Anyhow, let me continue with this theorem. Theorem statement goes like this. Suppose if EI is a sequence of measurable set in R, then we have to prove that restriction measure or measure of limit n tending to infinity, infimum of Fn will be less than or equal to limit n tending to infinity, infimum of measure of En. Meaning is, when you are going to take measure with En, you are going with infimum, you are going to get less than or equal to. Similarly, when you are going to take measure with suprimum of En, you are going to get greater than or equal to. So let me coming to the proof part. Let me prove this. I am going to prove the first one. So let me define a set F n such that which is collection of all E's. I have defined one set Fn such that which is a collection, or else I can say intersection of all E's. Now, just now I have told you, since we are dealing with infimum, right? So as I told you, when you are going to dealing with infimum, I have to consider a monotonically increasing sequence condition. So I can clearly write Fn is subset of Fn plus 1. So thus we have an infinitely increasing sequence of measurable set in R, and moreover we have already proved that if EIs are all measurable, then I can say, since it is a collection, right, so EIs are all measurable, I can say Fn is also measurable. Fine. I am telling you that since this is infinitely increasing sequence, moreover it is a collection of all, since EIs are all measurable, I can say Fn's are also measurable. So overall Fn is measurable infinitely increasing sequence. So if that was the case, just now I have proved you, in the previous session I have proved you and I have sent you the notes. You just go through the notes where I have proved one theorem for infinitely increasing sequence. Fine. So as per that theorem, hope so I have with me. See here. For infinitely increasing sequence, this is what the theorem I have proved in the previous session. So for infinitely increasing sequence, this condition holds good. Right? So I can rewrite where here I have proved for a set En. Now in this particular proof, I am taking it for Fn. So let me write this statement as it is. Instead of En, I am going to write Fn. M of union n is equal to 1 to infinity. Fn is equal to limit n tending to infinity m of Fn. Clear? Why? Because this statement is holds good only when infinitely increasing sequence of measurable set. As I told you, this is an infinitely increasing sequence since we are talking about infimum for the first case. Fine. And moreover, EI is collection of all measurable set. Since F is expressed as collection of measurable set, then Fn is also measurable. So measurably infinitely increasing sequence. Measurably infinitely increasing sequence. So we can apply this theorem. So this is per theorem. Clear? I have applied the theorem now. Now what I am going to do is, let me replace the value of Fn. Fine. I am going to keep this as it is. Union n is equal to 1 to infinity. Intersection I is equal to 1 to infinity. Fn is EI, right? Clear? sorry, this is infinity. I have defined an infinite sequence. Fine. Let me close this and I'll write RHS as it is. Now, just at the beginning I have told you the definition of infinitely increasing and decreasing sequence, or else limit supremum and limit infimum, right? See here, as per the limit supremum definition, it is intersection union. So when you have intersection union, I can write this definition. See here, but here I have union intersection. Remember, when you have union intersection, I can write that as limit n tending to infinity, infimum of En. Fine, I am going to apply the definition and I can rewrite this as m. I am going to keep as it is. I can rewrite this as limit n tending to infinity, infimum of En. Clear? I have applied the definition. So this term I can write this as limit n tending to infinity, infimum of En is equal to limit n tending to infinity, m of Fn. So let me take this as equation 1. Hope so it is clear. Now, what I have assumed is Fn is subset of Fn plus 1. Right? Fn is subset of Fn plus 1. Now, clearly I can write Fn is subset of En plus k. Right? For particular k. Why? Because Fn is subset of Fn plus 1 in the sense it is true for all the k's. N plus k number of sets. Anyhow, Fn is expressed in terms of Ei, and at the beginning itself I have told you, see here, if we are dealing with infimum, Fn is subset of Fn plus 1, then we can also write F as Fn is subset of En plus k. So I have used this definition and I have written Fn is subset of En plus k. Fn is subset of En plus k. Clear? Now, let me take measure for this. So you are going to get measure of En plus k. Again, at the beginning you just revise the video and you can see that whenever you have this, I can directly write this as, since it is condition for monotonically increasing sequence, so I have to apply infimum for this. So I can write infimum over k, measure of En plus k. Now let me take limit as n tending to infinity on both sides. So if I do that, I'll get limit n tending to infinity, m of Fn is less than or equal to limit n tending to infinity. I have told you when I am going to apply limit n tending to infinity, I can rewrite this as En plus k will become En for all values of k greater than or equal to n. Rewind this video. At the beginning I have told you, just go through that. So for all values of k greater than n, this En plus k become Ek. Clear? So this is what I have. Let me take this as equation 2. Now compare equation 1 and 2. We can observe that in equation 1, limit n tending to infinity, m of Fn can be replaced by this value. So let me replace this value with this. So I get m of, I am using equation 1 here, n tending to infinity, infimum of En is less than or equal to, I will rewrite this as it is, limit n tending to infinity, infimum k greater than n, m of En. It is understood whether you are going to write this or you are not going to write. It doesn't matter. Anyhow, let me rewrite this. M of limit n tending to infinity, infimum of En is less than or equal to limit n tending to infinity, infimum of m of En. So this is what we have to prove as per the first one. So you have to revise before going to prove the second one. Let me revise once again. Remember, when you're going to prove for suprimum, you have to take union and definition of infinitely decreasing sequence, and further I can write this statement as like this. Further, if you're going to take F as intersection of all the sets, I can clearly write En is subset of En plus 1k, En plus k is subset of En. As why? Because as Fn is En plus 1 is contained in Fn and Fs are expressed in terms of En. So this condition will be true. I can rewrite this statement as this. Now if I can take measure on both sides. If you take measure, I can write this as suprimum of k. Why? Because we are taking a decreasing sequence definition. Now when you are going to take limit n tending to infinity, as greater values of k, for k greater than n, let me mention here also, for all k values greater than n, this En plus k become m of En. So that is what I have told you. Now let me make use of all these concepts to prove the second statement. Now what is the second statement we have? Limit suprimum. Whatever we have proved in the first case is for infimum. Now let me repeat the same for suprimum case. I'm going to prove here. The proof is quite similar, but whatever the hints I have told you, you have to follow that. So first step is same. Now let me define one set Fn such that here infimum it is intersection. Suprimum you have to take union. So Fn is equal to union I is equal to 1 to infinity Ei. For each n belongs to n. All those things are same. Now I have assumed infinitely increasing definition. I have to assume for suprimum I am proving second one. For suprimum I have to take infinitely decreasing definition. Decreasing definition will be en plus 1 will be contained in en. Just the reverse of that. Clear? Now next step. Since it is monotonically decreasing sequence, moreover Ei is measurable. As I already told in the previous theorem that if Ei's are measurable, then I can say Fn's are measurable. So if Fn's are measurable and decreasing sequence, in the previous session I have proved this theorem. For a decreasing sequence, I can write this theorem directly. I have already proved this theorem in the previous session. So what I am going to do is, I am going to copy the same theorem, but in place of n, I am going to write Fn. So as per the theorem, I can write limit n tending to infinity m of Fn is equal to m of intersection n is equal to 1 to infinity Fn. This is as per the theorem. Clear? Now, next step, whatever I have done here, I am doing the same. Clear? Now, let me rewrite this statement, reverse of that, so that in order to avoid the confusion. So, Fn will be equal to limit n tending to infinity m of Fn. Now I have intersection. I have to prove for suprimum. So I have to take a union here. Let me take union, or else let me keep intersection as it is. N is equal to 1 to infinity. I can replace Fn with this. Let me replace Fn. So I'll get I is equal to 1 to infinity Ei, which is equal to limit n tending to infinity m of Fn. Fine. Now at the beginning I have told you the definition of suprimum and infimum. You can go through the video. So this I can write as limit suprimum, that is measure of limit n tending to infinity suprimum of En. If you understand first one, you can easily understand this. Limit n tending to infinity m of Fn. Fine. So let me call this as equation 1. Now since we have proved for infinitely increasing sequence, now we are proving for infinitely decreasing sequence. So I can write this statement as En plus k is contained in Fn. For decreasing sequence, I have told you at the beginning itself. Now I am going to apply measure on both sides. So measure of En plus k will be less than or equal to measure of Fn. Fine. Or else I can write this as suprimum, right? Suprimum of k, m of En plus k is less than or equal to m of Fn. Now let me take limit n tending to infinity on both sides. Whatever I have done in first case, I am doing the same. As n tending to infinity, limit n tending to infinity, suprimum of, for all values of k greater than n, I can write En plus k as En is less than or equal to limit n tending to infinity measure of Fn. Now I am going to replace this value from equation 1 as limit this value. So I can replace this term. I will keep this as it is. Limit n tending to infinity suprimum of k greater than n measure of En will be less than or equal to, I can replace this with measure of limit n tending to infinity suprimum of En. So now look at the second statement that we require to prove is measure of limit n tending to infinity suprimum of m into En. Suprimum of En is less than or equal to limit n tending to infinity suprimum of En. Anyhow, we have already obtained here. See here, just the thing is reverse of that. Let me rewrite this equation. I have obtained a less than or equal to b. Let me rewrite this as b greater than or equal to a. So let me do that. I can get measure of limit n tending to infinity suprimum of En is less than will become greater than or equal to limit n tending to infinity suprimum of k greater than n, or else let me leave this. So m of En. Now look at the statement 2. This is what we require to prove is. Hope so it is clear, but you have to remember all these basic concepts I have told you in the beginning of this video. Please go through this. Hope so it is clear. Now the next theorem is characterization of measurable set. It is very important and it is asked in the year 2017, but the theorem proof is bit lengthy. You have to understand the concept, then you can easily write. Here is a statement: for any set E in R, the following statements are equivalent. So if you are going to take any open set in E in a real number, we have to prove all these equivalent, all these statements are equivalent. In the sense 1 implies 2 and 2 implies 1, such that you have to prove. Anyhow, before going to the theorem, so as per the property of sets, what we say, suppose if you have two sets, one is subset of other. Let me take elements of A as 1, 2, 3, 4, 5 and elements of B as 2, 3 or else 2, 4. Whatever you want, you can take. Let me take 2, 3 only. Fine. Now let me calculate A minus B. That will give us 1, 2, 4. Fine. Let me calculate B union A minus B. B union A minus B will give us 1, 2, 3, 4. Right? Again you are going to get set A itself. So remember, if you have any two sets which is such that one is subset of other, then I can write one set as something like this, union of these two. Right? Similarly, the same property holds good for sets also. I mean open sets. Suppose if I have two open sets O and E such that one is subset of another, then I can write O as E union O minus E, something like this. So you have to remember this in order to prove the first one. Now let us prove the first one. Now go to the statement what we have. For any set E in R, the following statements are equivalent. So we are going to take a first statement is true. That is, we are going to take R is measurable. Fine, I am going to prove second one. Using first one, I have to prove the second one. Meaning is equivalent, meaning is I have to use first statement, I have to prove the second. First statement I have assumed. What it is? Let me assume, it is E. Let E is measurable. Let E is measurable. What we have to prove is, for any epsilon greater than 0, there exists an open set such that E is contained in O. In the sense, they are subsets, and moreover, measure of O minus E is less than infinity, we have to prove. Now, there will be two cases. First case is that when it is finite. Finite in the sense measure of E is less than infinity. If it is greater than infinity, we say it is infinite. Fine. So if measure of E is less than infinity, it is countable collection. Right? Now I have told you while explaining the property of outer measure of a set, look at just revise the notes and you can go through that. There will be some epsilon greater than 0 such that I have told you, look at the first property. There exists one open interval, set of open intervals, say In, such that E can be expressed as union of n is equal to 1 to infinity In. Fine, this is what I have explained. Concept of measurability of a set. See first property what I said. Suppose if you have A is a measurable set, I can express A as union of all open intervals. I have proved the theorem also. Right? So similarly here E is a measurable set, I can apply this. Then as per the translation invariant property at the beginning I have told you, if epsilon greater than 0 exists, then I can write length of In n is equal to 1 to infinity will be less than measure of E plus epsilon. This is also I have proved there. I have written clearly in the notes. If you want, you can check it. Fine. Now, what I'm going to do is, let me set E as O. Let me set open set also can be expressed as, if E can be expressed as union of open intervals, I can set O is also open set, right? Why? Because O is contained in E. In the problem itself mentioned that O is contained in E, they are subsets. So, if E can be expressed as union of open interval, O can also be expressed as union of open interval. And given, because let me write, given that O is contained in A. So O is contained in A, meaning is that they are what we say, subsets of one to each other. In the sense they are subsets. So as I already told you, when you have two subsets, I can write this statement as per the set theory property. I can write O is equal to E union O minus E. Fine. Let me take measure on both sides. So you are going to get measure of open set. It is not 0, it is O. Measure on E. Plus when you are going to apply measure, union will become plus measure of O minus E. Fine, let me shift this. So you will get measure of O minus measure of E is equal to measure of O minus E, or I can write measure of O minus E is equal to measure of O minus measure of E. Now let me take this as 1. Now what I'm going to do is, I have assumed O as union of ions, right? Let me take measure for this equation. So equation, let me take star. So I'm going to apply measure for equation star. That will give us M of O will be equal to M of union n is equal to 1 to infinity in. Clearly, union of in, measure of union of in, I have. When you're going to take measure inside, I have proved in countable subadditive property theorem. You can see that when you're going to apply measure, union comes outside and it will become summation, and equal become less than or equal to. I have told you this a number of times. So when I said measure, it is none other than length of an interval, right? So I can write this as n is equal to 1 to infinity length of interval in. Why? Because measure is equivalent to its length. Now look at the assumption we have made. Let me take this as equation A. From equation A, I can replace this length as less than m of E plus epsilon, right? So what I have obtained is measure of O is less than measure of E plus epsilon. Now let me take this as equation 2. Clear? Now anyhow epsilon is arbitrary quantity. Now we can compare equation 1 and 2. Look at equations 1 and 2. Look at equations 1 and 2. What we can write is measure of, let me write here, measure of O minus E is less than epsilon. Right? Why? Because see here, equation 2 can be arranged as measure of O minus measure of E is less than infinity. Right? Now this value is less than infinity, meaning is measure of O minus E is less than infinity. So that is how I have written this. Right? Now this is for the first case. When m of E is less than infinity, we have obtained this, in the sense finite set. That is, when m of E is finite, it is less than infinity, what we have obtained is measure of O minus E is less than infinity. Clear? Now that is what we have to prove also. Right? Such that m star of O minus E is less than infinity. See, when I explained the concept of m star can be written as m. M and m star are one and the same. When you have restriction, you cannot write star there. So if you are not going to write star, it doesn't make any difference. So m of O minus E is less than infinity, I have already proved here. For the finite case, countable collection of sets. Fine. Now case 2 is that when m of E is equal to infinity. When it is equal to infinity, what can we write? So as I already told you, when it is an infinite set, then there exists in a real number line, I can write real number line as in union of all the open intervals. Right? Where all ions are disjoint sets. I have proved this theorem also. Right? All ions are disjoint intervals. So if this is the case, then I can say by case 1 the result is obvious, right? By case 1 the result is obvious. Fine. Why? Because see here, in the case 1, what we have proved is E is expressed as union of all the open intervals. So for the first case, the result is true. That is, what we have proved is m of O minus E is less than epsilon. So if any set E is expressed as countable union of in, then in a real number R, since R can be expressed as union of in, E is also one of the set in R. So the same result holds good for the case 2 as well. So no need to prove, the result is obvious. Now let me prove what I have proved is first result implies second result I have proved. Now next we have to prove that second result implies third result. So let me prove that. We have to prove second result implies third result. Fine. That is, we have to take that for any given epsilon greater than 0, there will be an open set O such that, let me assume equation 2 is true. That is, for a given epsilon greater than 0, there exists open set O which is subset of E such that m star of 0 minus E is less than epsilon. So let me assume this statement is true, and we have to prove that equation 3, that is statement 3, is true. That is, we have to prove there exists G delta set such that G is contained in E and m star of G minus E is equal to 0. We have to prove. Now let me take epsilon as 1 by n. Since epsilon is arbitrary and n is also a small quantity, as we give values of n, it goes on decreasing, right? as we are dividing 1 into n number of parts, so the value will be very small, so that will be the value of epsilon. So it is arbitrary, we can take any smallest value that we want. Fine. And where n is a natural number, I can say. Now if that was the case, since by the assumption I can say there exists an open set On in general for n case, which is containing a set A such that m star of On minus E is less than 1 by n. What I have assumed is I have replaced epsilon with 1 by n, and I have generalizing the assumed case for each n. Now let me set. So we have to prove the third statement is true. Third statement is there exists G delta set. So as I already told you, G delta set is none other than collection, that is intersection of all the open set On. So what I'm going to do is, let me set an open set G delta set as G is equal to intersection of all the open sets On, in such a way that E is also contained in G. Given what we have assumed is E is contained in O. So now I have defined a new set G such that, which is a collection of all the open sets On. Moreover, E is also contained in On. E is also contained in O. So I can write, since G is expressed as On, O is containing E. So I can write G is also in E. It is something like, see here, E is, let me consider E as a set which is in set O. Now what I have expressed as G is a collection of all these open sets. If E is in O, then I can say E is also in G. Why? Because G I have expressed as O. So that is why this expression comes. Now I can clearly write that G minus E will be subset of On minus E. Right? What I have done is, if you are going to subtract, since I can write from these two expression, what I can write is G is subset of On. Right? Since G can be expressed as intersection of all the open sets, so from this expression what can I write is G is subset of On. On is a open set. What I did is I have subtracted an element E from this set. Fine. Or else I can rewrite this as On minus E is G minus E is contained in On minus E. One and the same, just I have rewritten the statement. Now let me take m star on both sides. So you will get m star of On minus E is greater than or equal to m star of G minus E. Or else I can rewrite this as m star of G minus E is less than or equal to m star of On minus E. But what I have proved is m star of On minus E is less than 1 by n. Right? That I have assumed as epsilon value is very arbitrary. It is 1 by n, very small quantity. So I can write like this. Instead, since each n belongs to capital N, that is set of natural number, for larger values of n, this value tending to 0, right? That is 1 by n. Or else if you want, I'll write one more step. I can write this as which is less than or equal to 1 by n. So as n tending to infinity, this value tending to 0, right? 1 by infinity will be 0. So as n increasing, this value will become 0. So I can write m star of G minus E is equal to 0. Now look at the third statement. What we have to prove is, if second statement is true, that is O is subset, E is contained in O, then we have to prove that for any open set G, that is G delta set. G delta set is none other than intersection of all open sets, which such that we have to prove this inequality, that is m star of G minus A is equal to 0. So that is what I have proved here. See here, m star of G minus A is equal to 0. What I have done is I have assumed second statement is true. Second statement I have already taken epsilon greater than 0 and E is contained in O. So that is what I have taken, epsilon greater than 0. There exists O such that E is contained in O, and since second statement is true, I can write the same statement as it is. Now what I have done is I have assumed the epsilon value as 1 by n, and let me replace it with 1 by n. Now we have to prove that there exists G delta set. So let me take a G delta set which is intersection of all the open sets. So from this expression I can write G is also subset of On. I have subtracted E from both sides and I have rewritten the given statement. I have taken a measure on both sides. Since we have assumed this value is less than 1 by n, so as n tending to infinity, we can note that this value goes to 0. So thereby I can write m star of G minus E is equal to 0. So that is what we have to prove. Hope it is clear. Now what we have proved is, so far 1 implies 2 I have proved. Clear? Next 2 implies 3 I have proved. Fine. Next we have to prove that 3 implies 1. Let me prove 3 implies 1. 1 is interrelated to other. 3 implies 1 we have to prove. In the sense we have to assume that this condition is true and we have to prove that E is measurable. Clear? Now let me prove 3 implies 1. In the sense I have to assume equation 3 is true and I have to arrive equation 1 is also true. Let me do that. I'm going to prove here. Let me assume equation 3 is true. 3 implies 2. 3 implies 1 I am going to prove. What I have already proved is 1 implies 2 I have already proved. I am going to prove 3 implies 1. Meaning is if 3 implies 1 is true, 1 implies 2. See here, 1 implies 2 is true. Fine. Again 3 implies 1 is true. Meaning is I can write 2 implies 3. In the sense 1 implies 2 implies 3 will be true. I am repeating once again. If 1 implies 2 and 3 implies 1, I can write 2 implies 3 as something like transitive property. So 2 implies 3. Fine. So I can write 1 implies 2 implies 3. Fine. So it is sufficient to prove 3 implies 1 now. So let me prove that. Now we have to assume equation 3 is, that is statement 3 is true. What is the statement 3 given? There exists, I'm writing this, there exists G delta set such that E is subset of G and M star of this equation is true. That is M star of G minus E is equal to 0. Fine. So I have assumed this statement is true. Now we have to prove that E is measurable. To prove E is measurable. Clear? Now I have already told you at the beginning of this session itself, you just revise. Suppose if for any two subsets, since G is subset of E, or else I can say E is subset of G, right? So if E is subset of G, I can write E as G minus E. I have given a counter example also, you please just go through that. So if for any two subsets, I can write E is equal to G minus E. Fine. Now from this expression I can write this part is measurable. G minus E is measurable. Reason is that in the statement itself we have assumed that M star of G minus E is equal to 0. We have already proved one theorem, measure of a countable set or measure of any set is equal to 0. By that theorem I can say this set is measurable. So why? Because I have already assumed in the statement. It is just a logic. So G minus E is measurable because given that M star of G minus E is equal to 0. Fine. So if this is measurable, then I have told you by the property of measurable set, if any set A is measurable, its complement A complement is also measurable. Right. So by that property I can say G minus E complement is also measurable. Now let me rewrite this equation as E is equal to G minus E can be written as G minus E complement. Why? Because if G minus E is measurable, its complement is also measurable. So I can write like this, or I can write intersection. So I have given counter example for this also. Remember, if you want you can take two examples. See here, can be written as G intersection G minus A complement. In the sense for any two sets A minus B can be written as A intersection A minus B complement. Both the expression is true. So this is from the property of the set theory. If you want you can take counter example also. So I can write this statement as this. Since G minus E complement is measurable, as I already told you, and one more theorem we have already proved, intersection of two measurable set is also measurable. Intersection of two measurable sets is also measurable, right? So by that property, since I have intersection of two measurable sets, so I can say E is also measurable. Since E is expressed as intersection of two measurable sets, therefore E is measurable. Hope so it is clear. Right? I have assumed equation statement 3 is true. Statement 3 is given that M star of G minus E is equal to 0. I have to prove that equation 1, that is E is measurable. I have to prove. In the statement itself it is given G is subset of E. So I have already told you for any two subsets I can write this property. Again the same can be written as like this. Since G minus E is measurable, as given that M star of G minus E is 0. So measurability of any finite set is 0. As per that property I can write this is measurable. If any set is measurable, its complement is also measurable. So I can write this complement is also measurable. Further, intersection of two sets is measurable. By the theorem I can say E is measurable. Why? Because it is expressed as intersection of two measurable set. So this implies equation 3 implies equation 1. So I have already told you if this condition is true, I can write equation 1 implies equation 2 implies equation 3. Fine. Further we have 4 and 5. Now let me prove equation 1 implies equation 5. Theorem is bit lengthy, but if you practice well, you can definitely remember. So I have to prove equation 1 implies equation 4. So I have to assume equation 1 is true. That is, let me assume E is measurable. So I have to prove that M star, if there exists epsilon greater than 0, there exists a closed set such that F is contained in E, such that M star of E minus F is less than epsilon, we have to prove. Let me come to the proof. Now what I have assumed is E is measurable. Now let me do here. Since E is measurable, by the property of measurability of set, I can say its complement is also measurable. E complement is also measurable. Fine. So if any set is measurable, its complement is also measurable. Now look at the equation 2, that is statement 2 given. So what is the statement 2 given? Given epsilon greater than 0, if for any set O, E is contained in O, then M star 0, O minus E, that is, O minus E is less than epsilon. Why? Because we have already proved that if statement 1 is true, statement 2 is also true. By the first case itself, we have proved if statement 1 is true, statement 2 is also true. Now, for proving this, I am using that concept here. See, what I have assumed is equation 1 is true, that is E is measurable. I have already proved that equation 1 implies 2. So I can make use of equation 2 here directly. See here, by equation 2, I have already proved this. 1 implies 2, I have already proved. So by that I can write by 2, what is the statement it is? So by 2, there exists epsilon greater than 0 such that O is, let me replace E with its complement. O is, when you are going to replace E with E complement, you are going to E complement here also. O complement, then such that I can write M star of O minus E complement is also less than epsilon by 2. Fine. Now what I am going to set is, let me set F as O complement. F is in any one of the set which is a closed set. F is closed set. Why? Because if O is open, its complement is closed, right? O is open set, its complement is closed. So F is closed set. Fine. So I have defined F as O complement. So if that was the case, I can write it as, again O complement is contained in E, right? Why? Because if E complement is contained in O complement will be contained in E. I'll write it once again. If E complement is contained in O, if you're going to take complement, O complement will be contained in E complement whole complement. That will give us O complement is contained in E. So that is how I have written this. Fine. Now what I'm going to do is, let me subtract it. I can write this as E minus F is equal to E minus O complement I can write. Fine. So E minus F is equal to E minus O complement. I have subtracted these two sets from a set E. So with this I can write, shall we rewrite this as O minus E complement? If you are going to take minus as common factor, anyhow is like, see here, it is something like if you are going to have open set like 1, 2, 3, 4, the notation will not be changed. If you are going to multiply minus sign inside, the notation of the set will remain same. Only the properties of set will change. So I can rewrite this as O minus E complement. So what I have obtained is E minus F is equal to O minus E complement. Now let me take M star on both sides. So you will get M star of E minus F is equal to M star of O minus E complement. Now what I have assumed is by 2, second statement, M star of O minus E complement is less than infinity. So I can write this is less than epsilon. So I can write this as less than epsilon. We have to prove equation, I have to take equation 1 is true, I have to arrive equation 4 is true. So I can write this expression as, if it is less than infinity, if it is less than epsilon, for any arbitrary, epsilon is any arbitrary value. Fine. Or else I can write this statement as M star of E minus F is less than, since this value is less than epsilon, I can write this value is less than epsilon. Fine. See here, look at the statement. I am repeating this once again. I have to prove equation 1 implies equation 4. Equation 1 is E is measurable. Equation 4 is m star of E minus F is less than epsilon. We have to prove. Fine. Since I have already proved that by first case, if 1 is true, second is also true. So by that case, I can write if E is measurable, E complement is measurable, it is well known. For if 1 is true, I can write this second statement is also true. So I have written the second statement as it is. But what I have done is I have replaced E with its complement. Fine. So that is why I have obtained this. Now, let me set F as O complement. Why? Because if O is open set, its complement will be closed. So F is closed set now. I have subtracted both from a set E. So for a complement set, closed set, I can rewrite this as O minus E complement. Fine. So that is what I have written. I have taken m star on both sides. Now as per the second statement, this value will be less than epsilon. So if this value is less than epsilon, I can write this value is also less than epsilon. And this is what we have to prove for statement 2. So what I have, for statement 4, see here, m star of E minus F is less than epsilon. M star of E minus F is less than epsilon. So what we have arrived is, I have assumed that statement 1 is true, that is what E is measurable. So 1 is true, I have proved equation 4. So this implies 1 implies 4 is also true. Clear? Next we have to prove that 4 implies 5. Fine. The statement proof is quite large, but you have to practice well. Last portion, that 4 implies 5. I am just revising. See here, what I have proved is first case. What I have proved is I have proved 1 implies 2. Next, what I have proved is 3 implies 1. See here, I have proved 1 implies 2. Clear? Next, what I have proved is 3 implies 1. So 3 implies 1. Next, what I have proved is 1 implies 4. Next, what we have to prove is 4 implies 5. Fine. So 1 implies 2, 3 implies 1, 1 implies 4, 4 implies 5. 1 is interrelated to each other. See here. So by these two statements, I can write 1 implies 2 implies 3. Fine. By these two statements, I can write 1 implies 5. So by combining these two statements, I can write 1 implies 2 implies 3 implies 5. If 4 implies 1 implies 4, I can write this as implies 4. So implies 4. Or else I can write 1 implies 2 implies 3 implies 4 implies 5. So this is the logic behind the proof of this. So I have already proved the first case, second, third. Now I have to prove 4 implies 5. Meaning is I have to take equation 4 is true. That is, given epsilon greater than 0, if this condition is true, I have to prove m star of E minus F is equal to 0. If it is less than epsilon, we have to prove that is equal to 0. Now let us see the proof. Now I am going to prove 4 implies 5. So I have to assume 4 is true. That is, you have to write all the statement. I am just skipping it. So for every epsilon greater than 0, there exists closed set such that F is contained in E and m star of E minus F is less than epsilon. So equation 4 is true. I have assumed. So I have to prove equation 5 is true. That is, statement 5 is I have to prove m star of E minus F is equal to 0. Fine. Now what I am going to do is, since epsilon is very small quantity, I can take value of epsilon as 1 by n. As in the previous case, I have done this. So as n belongs to n. So if you increase the value of n, this value definitely goes to 0. So if that was the case, I have already told you there exists a closed set Fn which is contained in F, such that I have replaced this. See here, m star of E minus Fn is less than 1 by n. Why? Because I have assumed epsilon as 1 by n. Now let me set F as union of all the collection of Fn's. So F is, I have assumed it as F sigma set, I can say. Why? Because we have to prove F sigmas, right? As per the definition, it is a union of all the closed sets. All closed set. And clearly by the definition of F sigma set, Fn is contained in F. This implies that E minus, let me subtract it from set A, is containing in E minus F. By the property of F sigma set, I can write, when you are going to subtract it from set E, since set E is the largest set. Why? Because F is contained in E. So you have to, when you subtract it from E, you have to reverse the inequality. Fine, as f is contained in E, I can write E minus Fn. I can write this as here E is subset of F, right? I am subtracting it from Fn. So when you're doing that, this inequation get reversed. Clear? And in this case, I am subtracting this set from Fn. Here I am subtracting this set from E. Clear? Now, if you do that, I can rewrite the given statement as, above statement as E minus F. Why? Because as E minus F is contained in E minus Fn is less than or equal to m star of E minus Fn. I can write like this. Why? Because see here I am writing this once again. This statement can be written as E minus F is contained in E minus Fn. Right? Just I have applied measure on both sides, then you will get this. See, m star of E minus F. This symbol will become less than or equal to as per the monotonic property, and I have written this as it is. Fine. Now what I have assumed is E minus Fn is less than 1 by n. So this value is less than 1 by n. So if this is less than 1 by n, I can write that this value is also less than 1 by n. So you will get m star of E minus F is less than 1 by n. So for larger value of n, as n tending to infinity, this value goes to 0. So I can write m star of E minus F is equal to 0. That's all. I have assumed 4 and I have proved m star of E minus F is equal to 0. So equation 4 implies 5. So this completes the proof. This is the characterization of measurable set. So last part I am repeating once again. I have assumed equation 4 is true and I have assumed this. Now I have set the value of epsilon as 1 by n, as it is arbitrary and very small. If you increase n, this value goes to 0. Now since we have to prove that F sigma set, as it is a collection of union of all the closed set, just I have replaced epsilon by 1 by n. This step comes from this. Fine. Now since I have assumed as Fn is contained in F, so I can write for at least one F, I can write F by Fn. I have replaced here for all n. So I have set the value of F in such a way that it is union of Fn, that is closed set. Why? Because F is a F sigma set as per the statement. Fine. Now I have subtracted E from the above step and I have taken measure on both sides. Since I have assumed that this value is less than 1 by n, then this value is also less than 1 by n. So for larger values of n, this value goes to infinity. As larger value of n in the sense this value goes to infinity, the total value reaches to 0. So I can write m star of E minus F is equal to 0. So that is what we have obtained. This completes the proof of this theorem. Thank you. Continue in the next session.